Hello, legends. This is Mr. Maze coming to you through our digital space, and I'm elated to be working with you today. Today, we're going to be working through the 8.2 video notes, and of course, 8.2 for us is going to be significance tests. We're doing it for proportions, but it's not for one proportion. It is for two proportions this time. So you remember 8.1, we were doing our look into confidence intervals for two proportions. And just in the same way that our 8.1 confidence intervals for two proportions problems had very much to do with what we did when we did single proportion confidence intervals with panic, we're going to see a similar trend here with phantoms and two sample significance tests for proportions. So you'll remember I told you when we enter this Unit 8, it's going to be all the stuff we've already done in Unit 6 and Unit 7, but we're going to revamp it. We're doing it with two samples and a couple of tricks come along the way. But if you'll have your slideshow up with you, you'll note on slide 20, the first part of significance tests for two proportions is the P. And the P in phantoms, as we know, stands for parameter. It's always going to be parameter. It was parameter when we did panic for confidence intervals as well. And for two samples, we have two parameters. We have P1 and we have P2. And when you go to write these parameters at the start of a problem where it says, is there significant evidence or is there statistical evidence or a good reason to believe X, Y, or Z thing, what you'll do is you'll set up P1 and P2, and you will start with, if it's a proportion problem, the true proportion of, and then of course I have ... there. And the reason why I have the true proportion of and ... is because you will then put context there based on the problem. So you'll say the true proportion of people who love the color red, the true proportion of really dope guitar players who love to teach, the true proportion of those who tell the truth because they believe in the sanctity of what is accurate. Okay? Whatever that may be, you're going to set those two parameters. Okay? And that's step one of phantoms. And step two is your hypothesis. Now, I want you to notice so far, everything's been pretty smooth. We're, instead of doing one parameter of interest, we have two, but otherwise we're rocking and rolling. When we get to our hypotheses, we're gonna have two, just like we did with one sample. The first one will, of course, be our null, the HO, and the other will be our alternate, the HA. Now, one thing to take note of is that at least in Stats 101, right? So in AP statistics, our null is almost always going to be P1 equals P2. The idea is that there is no difference between these parameters. Another way to write that, I'll just say or, is P1 minus P2 is equal to 0. Both of these are equally valid. And if you were to hypothetically write either one of them, I would accept either, as would AP. So take your choosing and live the dream, right? Something to note here, and this is a good pause moment, is that the reason we're looking for no difference is because in higher level statistics, sometimes we are looking for a definite difference. And there's a possibility that AP might have a problem that's challenging, or that I might throw a challenge problem where the null is not that P1 equals P2. And in those particular instances, there's a thing we're going to do in a moment that we won't be able to do for those instances. But for our purposes right now, we are expecting almost always for the null to be then P1 is equal to P2. Our alternates are as they've always been. We're on slide 21 right now, and you'll note that the three big options are P1 is greater than P2, P1 is less than P2, and P1 is simply not equal to P2. Now, mind you, because there's P1 and P2 here, you could do the same thing where you do P1 minus P2 is greater than 0, P1 minus P2 is less than 0, and P1 is minus P2 is not equal to 0. It depends on how you want to structure the problem. All of those are possible, okay? And a thing to put as a side note here is to remember that, and I'll write it as a side note, keep track of what you choose to be your P1 and what you choose to be your P2, and structure accordingly. And what I mean by that is, similar to previous units we've had, where we had like random variable distributions, and we were looking at adding and subtracting those distributions to find the difference in sales, for example. When we do these calculations between these two sample proportions, what we need to be certain of is that we are tracking the right thing. So if we assign P1 to the value that's greater, be sure that you're looking for a greater than value, for example. Does that make sense? It should. I think you're locked in with me. All right, so we have P and we have H, right? And you can see on slide 22, I go into a little bit of detail, right? But all I'm doing is saying exactly what I said here. The argument is that we are assuming in our significance test that the null hypothesis is true, and the null will always be that there is no difference visible. Now, slide 23 is where something new pops in, right? So I'm going to swap colors. We're going to go to blue, and I'm going to put a star over here. The concept here is what's called a pooled proportion. And I will warn you, because a pooled proportion requires the variance or standard deviation of the two samples to be equivalent or close to equivalent. Only, and I mean this, only for the most part, there may be one exception, but for the most cases that we deal with, only going to use this for hypothesis tests. And as we go on to go over in the 8.3 notes, we only use it for hypothesis tests for proportions. We don't even use it for hypothesis tests for means, at least not in this class. It can be used for means, and we'll talk about non-Welchian versus Welchian distribution situations and conditions. But the reality is it's almost always used significantly in a hypothesis test for proportions, right? Because only in proportions, which are inherently bimodal, and binomial in nature, right? Like we only have two options right here. And actually, I shouldn't say bimodal, but they're inherently binomial in nature. And because of that, we know what the binomial structure will look like for either one of the sample distributions. We can't say the same thing about means. But anyway, I'm getting a little big for my britches. Let me get back to this concept of pooled proportions. We're going to pool our proportion. What that means is we're going to take our initial situation, which was p hat 1 and p hat 2, which we know we're finding the difference between. And we're going to create a third proportion. And that third proportion is called p hat sub c. And the c stands for combined. Okay? And what c hat sub c will look like is number of successes from p hat 1 plus number of successes from p hat 2 over sample size of p hat 1 plus sample size of p hat 2. And effectively, what the pooled proportion is, it's going to act kind of like our null for the standard error and for approximately normal checks. Okay, so the two things, the sole two things you will use and let me highlight it now. The sole two things you will use your combined proportion for are going to be the standard error calculation and the check for approximately normal, okay? And it should make good sense. The reason we do this pooled proportion check is we want to have the most accurate metric for our sampling distribution. And as you know about our sampling distribution, it's based around the null proportion. But in this case, there is no null proportion. We have two sample proportions, and our null proportion is effectively 0. The thought is that there will be no difference. So what we want to do is we want to base the sample size of our distribution on N1 plus N2. We want it to be all the people we surveyed. Now, the only proportion that actually makes good sense to use where the denominator would be N1 plus N2 would be a combined proportion, because otherwise we wouldn't really know what to do for that average. If we want to find the total number of people, there's really no numerator that would make sense except to simply add X1. Remember, X1 is number of people that said yes in p hat 1, and X2, number of people who said yes in p hat 2. Hopefully that makes sense. If that doesn't, I would heavily recommend finding me to touch base, because of course it is an important concept, and as always in this class, it's more important to me that you understand why we do what we do than simply to understand that we do it. Okay, but I want you to know something. Now that we have figured out pooled proportions, we are good to go, Legends. We're going to get right back into the stuff that makes perfect, obvious sense, that follows everything we've done so far. So if we head to slide 24, we are moving on to the A in phantoms. Just as easy as that. Now the A is going to follow suit with what we've always done. The first part of the A is it random? It should be stated in the problem. Second part of our assumptions will be, well, is it independent? And of course, we know the rule for that is if you do 10 times the sample size, that should be less than the total population. Now, the thing I want to make clear here is there is a sort of alternate perspective. Let me do we'll do this one in green. An alternate side of things that you may find, all right, or is instead of random and independent, sometimes because we're doing paired proportions, right? Well, not paired, I should say. We're doing two samples of proportions, right? Because we're doing two samples of proportions, we're in a situation where we might get an experiment where there's a treatment group and it's randomized, right? We've randomized treatment groups. And, placebo group, for example. If it says that, you don't need to do these guys. Okay, so if it says we do an experiment or we set up a treatment group and a placebo group or a regular group, if they say we got volunteers and we randomize them to one group or another, suddenly the only thing you have to write instead of random and independent is that we did an experiment with random treatment groups. And then you're done, okay? So either you're getting a normal problem where you have two different proportions from two different populations or from two different subsets of the population. And then you go ahead and you just do 10 times your sample size. Remember, you'll have to do 10 times N1 and 10 times N2. Okay, both of those must be calculated to make sure that we're good to go, so to speak. Okay, so you'll do that. Or if it's an experiment with random treatment groups, you'll just say that. You'll say experiment with random treatment groups and you'll leave on your merry way. And then the third part of assumptions is the one we already know, which is checking for approximate normality. And as I said on the slide before, on slide 23, when we were looking at pooled proportions, this will be based around our pooled proportion or our combined proportion. So as you can see on slide 24, our options are N1 times P hat C, right? Not P hat 1, not P hat 2, but P hat C. N1 times 1 minus P hat C. And then N2 times P hat C. And N2 times 1 minus P hat C. All of those must be greater than or equal to 10. And if that's the case, solely for proportions, then we are good as the house of Gucci. Okay, not the movie, but the idea. Okay, hopefully that makes good sense. Remember, we must use the pooled proportion because we are assuming the null is true and there's no difference. So we want to make a proportion for approximate normality that works with our entire sample set. And we're done with approximately normal, and we're done, in essence, with our assumptions. Now we go on to name. Let's get back to our beautiful color orange. Gosh, I love the color orange so much. All right, we are on to N. Name it. What do we name it? This is always the easiest part. You will call it a two-sample z-test. Remember, it is a test. And because we already set up our parameters, P1 minus P2 can be written with ease, and we're good to go. On slide 26, we move on to T and we move on to O. Now, really quickly, I'm actually going to combine T and O for us here. If you take a look at slide 26, you will see the formula that we're using. So if there is an algebra equation, right, or if there's a multiple choice problem where they want you to pick among various test statistics, remember this is our z-test statistic here. The formula and the format will be P hat 1 minus P hat 2. Because remember, that's our numerator. That's going to be our sample statistic. Minus the parameter, which will always be 0 if the difference is none, over our standard error. And remember, our standard error is going to be the combined variances here, but it's going to be based around, like we said above, the pooled proportion. So odds of success times odds of failure over sample 1 size plus odds of success times odds of failure over sample size 2. Okay. This is equivalent, by the way, to the following. Same numerator, of course. Oh, no, that's P hat 1 and P hat 2 minus 0. Over, and just for my algebra geeks out there, because sometimes they like to phrase it this way, we pull out the pooled proportion times 1 minus the pooled proportion. And then we do it times 1 over N1 plus 1 over N2. Either of those are acceptable, and both of those might show up as the framework for a multiple choice problem where they're like, which one of these is the correct test statistic for a two-sample z-test for P1 minus P2, okay? But for our purposes on most of our problems, if you slide over to slide 28, we do stat. We go to test. Remember, now is about the time to get really comfortable with your calculator functions. And we're going to do not one, but two prop z test. And then you're good to go. When you do two prop z test, you will plug in all the values you expect. Number of successes 1, number of sample 1, number of successes 2, number of sample 2, and then you'll be able to plug in your sign. Does P1 equal P2? Does P1 greater than P2? Is it less than P2? Or is it not equal to, depending on your alternate hypothesis? These steps are detailed in more of a close look on slide 29. Excuse me, and of course we're going to terminate with MS. Should be a relative breeze. And of course our options are we have to compare the p-value first. So the p-value is equals something that's either greater than or less than or not, or I almost said or not equal to. Mr. Mays, you fool. We're not setting up an alternate hypothesis here. We're comparing a p-value greater than or less than. The alpha, which will equal something. If it's not stated, it will be 0.05, but otherwise it's just something, right? We don't know, whatever it's set up in the problem to be. Maybe it's an alpha of 1%. Right? And then we will state that we either reject, you must state all of this, that we either reject or fail to reject the null. And then we either have or don't have convincing evidence. And I would structure this in a way that makes the most sense for you, for the alt. And be sure that you give context for the alt here. That's super important. Now you'll notice this structure is exactly the same as it was for one sample, Z tests for proportions. That's why I'm zooming through it so quickly. And that's actually why these notes are going to be pretty quick. So what I would recommend right now is if any part of this doesn't make sense, go through and watch one sample hypothesis tests for proportions, and then come back to two sample. Because the only shifts that we're going to notice here are the pooled proportion, right? That's one shift. This guy. And more importantly, this guy, the pooled proportion. And the second shift is simply having to run two parameters and go through and run a 2 prop Z test instead of a 1 prop Z test. Okay, when we interpret the p-value, you should know this. This is on slide 31. Assuming the null is true, this is for interpret p-value. And again, this is in previous video notes as well, so you've already got this. But let's one more time for the cheap seats. Assuming the null is true, give me context, right? What is the null? And blah, 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 blah. The probability that we observe our, and you have to say our sample difference instead of our sample statistic. But remember, it's your sample statistic or sample difference or more extreme. A lot of people miss this on the FRQs for Unit 7's test. So or more extreme, I'm gonna highlight that. I'm gonna highlight that in perp. Perp, my goat. Or more extreme, do not forget or more extreme, is the p-value. So state your p-value. Put that in there and you are good to go. And that's how we interpret a p-value. And from there, you will note slides 32, 33, 34, and 35 offer you opportunities to practice these concepts, okay? They should be pretty straightforward. And if you have any questions about them, come find me and I will answer them for you. But I just want to be clear, and I'm really thankful, right? You should notice these are pretty quick slides. This unit, even though it is a 4-day content unit as opposed to our normal 3-day ones, you're going to notice it's pretty smooth sailing, right? We're doing 4 days of content, a review, and then an exam. And you even have your quiz on just the probability stuff. So this 8.2 and the 8.1 video notes. But all it is running back through being able to conclude a hypothesis test, being able to test a hypothesis test, in this case with 2 prop z-test instead of 1 prop, being able to name your test, being able to check for approximate normality, independence, and randomness. Although remember, because we have 2 proportions here, we have the chance of having an experiment, in which case you don't have to say the 10% rule or random, you just have to say an experiment with randomized treatment groups has been done, and that takes care of the first 2 steps of assumptions, leaving you with only checking for normalcy. Remember that when we check normalcy for a 2-sample z-test for proportions, we do it using the pooled proportion, which we create over here, where we do both of our success numbers added together over both of our sample sizes added together. The reason we do this is we want our sampling distribution to be based around the total number of people we actually interviewed, and the only way to make a proportion that accurately represents that, amid looking for a null proportion of 0, is to take all the people who said yes to both p-hats over the total number of people who we were interviewing in both p-hats. We then went through and did our hypotheses, which are the same as they were last unit, except now it's involving P1 and P2 instead of just one proportion. And then, of course, we finished in reverse order with our 2 proportions of, remember, it's the true proportion of blank and the true proportion of blank. These will be our 2 parameters that we mess with. Legends, I'm so proud of you. Go through these notes, and if anything doesn't make sense, ask me questions on Remind, reach out to me, and then do go back through the Unit 7 stuff on proportions to make sure that it's all coming together. Ever forward, this is our last big push unit for inference, and then we finish up with chi-squared and regression in Unit 9, and there's some tricks up my sleeve there too. It's a rough time in the best way, but this is our last push on some of the hardest content of the year. So whatever you do, don't sleep now. This is the unit to really clock it in. Last unit was the unit to make sure you were awake. This is the unit to say, it's morning, Mr. Mays, and I live the dream every single moment of the day. I'm proud of you. Thank you for being my students. This is Mr. Mays, with all the love in the world for you, signing off.